said, I was reading Schutz, and it said, so I'll just read it out to you, but it said a particular sentence that did not make sense to me. Just I'll just read it out to you. So it says, these are two regarded vectors tangent to different curves. Curves that are different parameterizations in a region of that point. A curve has a unique tangent since the path is parameter given. So basically saying infinite curves of them and like
yeah, for every path there are infinite curves, and each one of those curves has a different tangent. All of those are parallel but have different magnitudes. So if you for example have a field of tangents, all of which are, let's say, unit tangents, you'll get the path, but you won't get the parameterization. If you were to be given a proper tangent vector and be told that this is in a given parameterization, then you will get the parameterization.
And then the curve, hence the curve.
And hence the curve, not the path, not just the path. Yes.
एक ही बात की दो डिफरेंट कर्व्स हैं, वो डिफरेंट पैरामीटराइजेशन होती है। तो जब हम कोऑर्डिनेट सिस्टम डिफरेंट लेते हैं तो क्या होता है?
तब पूरी स्पेस में जो आप कोऑर्डिनेट रख रहे हैं वो डिफरेंट होता है। सो कर्व है क्या, पहले ये सोचें, राइट? कर्व ये है कि आपके पास एक पैरामीटर है, and if it helps you, think of it as time, right? For each value of that parameter, you give me a coordinate set, a point in that coordinate direction, and so then you will get each of the coordinates as a function of that parameter. Right? So that will not only give you a path but also a curve. If you were to change the parameter, you change the curve. Same path. So coordinate system change करने से coordinate system change करने का मतलब ये है कि आप जिस तरह से change करते हैं ना उसको क्या होता है coordinate नहीं, ये जो components, एक वेक्टर के components इस तरह से change होते हैं ना, वो उस तरह से change होते हैं, ठीक है? जब आपने एक सिस्टम फिक्स कर दिया तो उसमें जो भी वो वेक्टर है वो एक कोऑर्डिनेट सिस्टम में गिवन है। तो कोऑर्डिनेट सिस्टम चेंज करने से जैसे वेक्टर चेंज होता है वैसे वो चेंज होता है। वेक्टर विल रिमेन द सेम, राइट? बिकॉज द सेम पैरामीटराइजेशन एंड द सेम कर्व, सेम पैथ, सो सेम कर्व। सो टेंजेंट वेक्टर चेंज नहीं होगा, लेकिन अगर कोऑर्डिनेट्स चेंज किया आपने, देन इट विल ट्रांसफॉर्म द कंपोनेंट्स ऑफ दैट वेक्टर as by our formula, whatever the formula. Second? Tangent vector. So the vector itself does not change. Yes.
So our generalized coordinates, as we do in classical mechanics, are coordinates in the sense that we talk about in relativity.
No.
So they do not form a coordinate system.
Yes, they would form a coordinate system in the phase space, but along with the momenta, but no, not necessarily in space. Not necessarily. Well, there might be constraints.
Yeah.
Okay? And so they would describe a subsurface, a hypersurface. Subsurface is called a hypersurface. Hyper having no allusion to any super. Hyper? Can that be hyper? Yes, that can be hyper. Yes, good.
Do you know if the word hyperprotein that we cannot realize?
No, I don't know. You do, maybe. I don't know. That's one of the things that you develop as you come out of your childhood. Okay, so today we're going to talk about the metric. You guys remember? So I'm not going to go into what metric is, you know everything. And you know all of the relations possibly that I'm going to write on the board. So I'm not sure about you guys, but so a metric is a 0-2 form, okay? It's a special 0-2 form. It is symmetric, and we choose it to and once you choose it, it gives you all of the lengths and geometrical properties in that space. Okay, most probably you guys also know. For example, so for example, yesterday or the last time we were talking about that this thing is 1, right? How do we know that this thing is 1? We have to use the metric. And so the metric, for example, in Cartesian coordinates. So this thing is, for example, this object is the metric, and its components are given by this relationship, right? And so that's how we define the metric if we know the dot product already, or we can define the dot product via the metric. So you could say that this thing, we say that this thing is delta alpha beta in Cartesian coordinates. Cartesian. And then say that A dot V is equal to G A B, or something like this. Right? So you could define the dot product like this, or you could define the metric by the dot product if you know the dot product already or whatever. Right? So you have to somehow specify the metric. Once you have it in one of the coordinate systems, then since it's a tensor, just by transforming it as a tensor, you can get it in any coordinate system. Okay. So, okay, so this is going to be the starting equation for us. Okay, and so this is, by the way, these are the components of the metric tensor. And so if you want, in Cartesian coordinate system, this is 1, 0, 0, 1 as a matrix. Okay, remember we're in R2, right? So this is 1, 2, 0, 1. In Rn, this would just be an n by n matrix with the same property. Okay. So anyhow, so for example, how would you get? There are at least two ways of getting the metric tensor in, let's say, polar coordinates. So can somebody give me one of them? I just gave you one. Like a minute ago. Yes.
Shall we put in the basis vectors in?
Yeah, that's so the alpha beta prime, right? So this is equal to G, and now you put alpha prime and beta prime, right? These are the basis vectors in the polar coordinates. Okay. And so how can we use this to calculate the metric tensor? And now the question, yeah.
You are asking for this.
So if
it will be
so
transformed in polar coordinates.
yes, so this E alpha, E1 prime is ER, and E2 prime is E theta. Right? So now how would you calculate the components? Like here we calculated them to 1, 0, 0, 1. What are the components? This G alpha beta. These are numbers, or these are functions. How would you calculate them using this expression?
By cos.
The dot product of the basis vector. ER into ER, ER into E theta.
I was asking how can we use this? Okay, so this is a linear. So the thing that I want to say is that this is a linear function, and we could write these as functions of ex and ey. We already know what this thing is, and so using that we can calculate this. The other way would be to calculate these by using this relationship. So do you know these?
Yes.
These are these objects,
Yes.
and you know these,
Yes.
and so you can calculate. So these are two independent, well, these are two ways that you can sort of go about doing this. There's another way that also uses the dot product. All of these are related. Right? Should I tell you what I'm talking about here, or you guys are okay with this? What I made this say? Right? So how would you use? What does it mean? What do we mean by saying that this is a linear function and that will help you calculate that?
We can write it in terms of Cartesian coordinates. The polar coordinates can be written in terms of Cartesian coordinates, and we have done that in previous.
Well, these are basis vectors, not the coordinates.
Yes.
But we've done that,
Yes.
right? For example, yeah. Second. So, for example, ER was written as cosine of x, ex plus sine of theta, and sine of theta ey. Okay. So, how does that help you calculate GRR, for example? So, this is going to be G cosine theta ex plus sine theta ey, comma, cos of theta ex plus sine of theta ey. And now, what should I do? Dot product. Again, you guys are after the dot product. I'm saying just use this property. Use this as.
Yes.
You're not allowed to use the dot product.
Use linear.
So how? So then how? So this thing, since this is linear, it will become cosine theta ex, comma, cosine theta ex plus g of, and then all of these. There are four terms. So, for example, here you will have ex and ey. So this will go to 0. Ex will go to 0. And then there will be a g sine theta ey, sine theta ey. And since these are linear, so this cos of theta is going to come out, cos square. And so this will become g ex, and that's 1. And plus sine square of theta, the same 1, and so you get cos square theta plus sine square theta, answer is 1. Okay? Homework. Using this method, show that g e theta is r squared, and g e theta er equal, and so this is g theta, and this is GRR. Okay? And so this thing, G theta R, is equal to G E R E theta, which is GR theta, this is 0. Homework, do that. Okay? Anyhow, whichever way you choose to go. I mean, you can define the dot product now in terms of this. Okay, so G alpha beta in polar, so this is going to be 1, 0, 0, most of the metrics that we'll deal with are going to be diagonal. But there are matrices. I mean, this doesn't necessarily have to be 0.
X1 is 0 because of automatically.
Yes, the
Automatically.
yeah, the basis vectors are orthogonal. By not saying that the basis vectors are orthogonal is basically just saying what the metric is. So, okay, so once you have G alpha beta, you can, and so this is whichever one you want to call the metric, but we call this the metric, and the one with the upper index is the inverse metric. And so we can define that as a matrix if you want, or you can define that as a tensor by this equation that G alpha beta, G zeta delta is delta alpha. Right? And so this will become 1, 0, 0, 1 over r squared.
So how did it become 1 over r squared?
You tell me.
For it to be inverse.
Yes.
For this equation to hold true, that
Yes. Anyway. Okay, the two things that come immediately after you have the metric is that now you can talk about lengths and volumes, and the other thing is that you can have a correspondence between vectors and one forms. Again, by show of hands. Vectors and one forms. Okay. So these two things, let's just discuss them very quickly. So if I were to take these two vectors, this vector, and put it in here, so this is basically G alpha beta, dx alpha, dx beta. This is the infinitesimal length, right? And so let's define this as ds squared, or simply it can also be written as the dot product between these two vectors. For some reason I'm writing dl dx, right? And so so if you already have decided what this infinitesimal length square is, or somehow you've sort of some information on that, then you basically have information on G alpha beta. So for example, if you write this in Cartesian coordinates, right, then these coefficients are the, so let's do like this. So this is Gxx, this is Gyy, dy squared, and then there's Gxy, dx, dy, and Gyx, dy, dx. Right? And I've just opened this up. Right? Everybody understands how these two are related? Right? Okay. So if you just compare this with dx squared plus dy squared, then you know all of these. So you know that these two are 1 and these two are 0. Okay? So we could do the same exercise with polar coordinates. And what is dx in polar coordinates? Neha?
It's
dr.
dr plus r d phi, more d theta.
Yeah, r d theta. Okay. Right? Or better write it like this. dr r or er. And r d theta. Right? And so the dot product, and so this will give you dr squared plus r squared d theta squared. And so this is GRR, and this is G theta theta, and GR theta and R theta are 0. I'll talk about the volumes later.
So dx over here is a small vector rather than any small vector rather than the small vector along x.
Take it.
So dx over here is not a small vector along x rather than any small.
Oh,
vector.
yeah, that's why I was writing it dl. So if you want, you can write it dl. It is the same notation that we're using in Q of t. X is the position vector. So, yeah, maybe that's better. And another thing is the path from vectors to one forms and vice versa. So, how do you go from a vector to a one form if you're given the metric? Could you do that if you were not given a metric? You don't know?
So a question along this, initially we were not using the dot product to define the metric, but just right now, when you use the argument of
So where does the metric come from? That's the question that you're trying to answer. So what happened that we suddenly know what the metric is? Right? I don't know. So you will have to tell me first what the metric is in this space. Right? If you were to take R2 and put a different metric on it, so when you put a metric on a space, it brings a structure with it. Right? Before the metric, you don't know the distance between points. So you know that which points are neighbors of which, but whether the houses are small or big, right? Whether they're poor people or very rich people, so big houses, that comes with the metric.
So when we had the inverse.
So first you will have to tell me the metric. So I just gave you the metric in that first line where I write delta alpha beta.
So for dx you use the inverse metric because now it was defined, right?
No,
I use the argument of
I'm
dx.
not using the inverse metric, I'm still using the metric. The way I've written it, with the lower indices, it's still the metric, right? And so where did it go? So on the other book. So in GR, it's a good thing that you asked this question. It's still using the metric, right? And this is exactly the question now, how to go from. So for example, this thing is equal to g alpha beta, dx alpha, dx beta, but now these are one forms. Components of the one forms, right? And yeah, I was going to say something. So that's what GR is all about. You give it, so you have a theory where if you specify the energy momentum tensor, it tells you what the metric is. Right? So metric for you is basically like metric is basically the field that you're trying to determine. So in classical mechanics, if someone gave you this equation with some initial conditions, your job is to determine the position of the particle for all times. Let's see how otherwise. So the corresponding thing in GR is that you're given, so here you're given a force, right? So in GR you're given an energy momentum tensor, right? And it gives you the corresponding metric. So it tells you, for example, what is the distance between points? What is the structure of the space that you're living in, or that you're talking about? Okay. So, yeah. Okay, anyway. So yes, so the question that we were trying to address was, and let me come back to that start. What is the correspondence between one forms and the vectors? No? Okay, well, one of you should know.
And you can go from one form to a vector using a metric.
Yeah. So the metric gives you one. So if you're given a metric, let's start with. So maybe this needs to be said once more. So if you give me the metric, it has two slots, right? And so if I put a vector in one of these slots, the other slot is still empty, right? If I put a vector in the other slot, it gives me a number. But what is the property of a one form? You give it a vector, it gives you a number, and it's linear, blah, 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 everything. So this whole thing is a one form. This one form is given the same name as this A because sort of it's coming from this A. And since the metric is symmetric, it doesn't matter whether I put A in this slot or in this slot. In general, it doesn't matter, but not in the case of the metric. Okay? So the corresponding equation in index notation is this. That if you have a the components of a vector, then this thing gives you the components of this one form. So if you have the metric, you can go back between vectors and one forms. You can sort of make a one-one correspondence between the space of vectors and the space of one forms. You can take a vector and you give it a one form. That's your one form. And you can do this with all the vectors. And we've proven earlier that the space of one form also forms a vector space. In fact, the space of all tensors form vector spaces. You guys remember that? All of that tensor algebra?
Yes, we did.
We have done all of the tensor algebra. Okay. And so this is, so an example would be that d phi in a given basis, what was it? Partial phi by partial, let's say partial r, and partial phi by partial theta. Right? Okay. And so how do I generate this? Right? So it will be, and now this is a vector. Usually when you use gradient, and when you talk about gradient and all that rate of change, that's vector gradient, not the one form. Okay? And so this alpha is just going to be d alpha beta d phi beta. Okay? So for example, since the metric in polar coordinates is diagonal, so you have a sum over r and then theta. So only r term is going to contribute, and so this is going to be partial phi over partial r. r is 1, and so this is partial phi by partial r, and d phi. So this is d phi r.
So, confirm vector word.
Second?
Now confirm G5 R department. So after this application.
Yeah?
You put a tilde on D
And theta is g theta d phi by dr. And now you see where this 1 over r square comes from. Right? There's a 1 over r square in your vector. Right?
but in order to do the opposite, we have to use the inverse.
Yeah.
And
Metric and the
this-
inverse metric, you don't sort of differentiate it. You have the same information.
They do have the same information, but then we have to work it out like this.
Yeah, you have to have the indices in the right place, always. You can't have alpha on the downstairs on the left hand side and upstairs on the right hand side. Okay. EX, right? What is this thing? So if you try to differentiate this with respect to, let's say partial by partial theta, what should this be? How many of you say this is 0? Only one brave soul. You're the bravest of them. Yes. Okay. What is EX in polar coordinates? What are the components of EX in polar coordinates? It should be lambda Rx and lambda theta x, right?
Yeah, so
And so this is, just a second, so this is cos of theta, R inverse. You raise your hand? No? What do you have in front of you?
Sir, I did not choose. It says
Choose
zero.
cos.
It says zero says Rules of relativity are possible.
Most clever of the class is not.
सर लेकिन मैंने जीरो स्पेस नहीं कहा था मैंने इंट्यूटिव नहीं कहा था मुझे जो लग रहा था मैंने कहा था फिर मुझे मिला था आप ट्रांसफर करा
मैं पूछ रहा हूँ क्या होगा ये? Zero is the right answer. क्यों नहीं क्यों होगा zero? और ये क्यों नहीं zero है?
क्योंकि इसमें R भी है।
ओह अच्छा इसमें R
थीटा है, उसको R पे डिवाइड है। EX
तो R भी तो नहीं ER भी तो चेंज है तभी ER direction change करनी है. Fine. Okay. Then the question again, why is this not zero? It should be zero.
बेसिस वेक्टर भी है।
Very good.
ट्रांसफॉर्मेशन
तो यही तो मसला है कि आप अगर इसको अंधाधुंध डिफरेंशिएट करने की कोशिश करेंगे, you'll get it wrong. Okay? Yes. So this should be zero, and this is your homework. Right? And A is a parameter, by the way. So A the function of lambda, and so this is d by d lambda, and I can write this vector A as A alpha, E alpha, right? And in Cartesian coordinates, this doesn't change. And so I can write E alpha dA alpha over d lambda. Right? So this is Cartesian.
So lambda is a new coordinate, a new basis, some new basis.
Say it again. Say it again.
Like the way you said that d by dt of dx is zero. So you over here you're saying dA by d lambda is by lambda you
Okay. So, but you guys remember that we had, did we talk about that or not? That when you differentiate something, so if it is an mn tensor, you convert that to an mn plus 1 tensor. Guys remember that?
Yes.
Did we talk about it? Yeah, maybe we did talk about it. So what about this one? Is it a vector? Are these the components of a vector or the components of a 1-1 tensor? Components of a vector. Why?
because they are given with respect to basis.
Yes. So this is just a number, right? And so the difference of between two vectors is just a vector. So this thing is a vector, right? Okay. Okay. So you guys remember when this was true? Come back to it. Okay, anyway. So this statement is not true in general. There are some courses where you have, well, there is one course where you have to calculate maybe some mathematics or mechanics, where you have to calculate, for example, the acceleration in polar coordinates, and you get these horrible equations. So partial by partial r of ER, what is this equal to? Well, this thing is equal to partial by partial r of cosine of theta EX. Now, you see, it's just very convenient to write things in terms of EX and EY because their derivative is 0. Yes. And so, plus sine theta EY, and the derivative is? Oh, ER, you just said ER changes.
No.
You know? Yeah. Does anybody? So d by d theta of ER is d by d theta of this whole thing, which is equal to minus sine theta EX plus cos of theta EY. Right? And so you can see that this thing is E theta over R. Okay. Homework, show that partial by partial theta of partial by partial r of E theta is equal to 1 over r. क्या हो रहा है? Partial by partial r of ER ये 0 क्यों है?
सर वो थीटा के जो कंपोनेंट है वो आपके ऊपर डिपेंडेंट के बेसिस बाहर आ गई
फिजिकली ये 0 क्यों है? r के क्या हो क्या रहा है? फिगर में क्या हो रहा है? प्लेन में क्या हो रहा है कि ये 0 है?
सर आर अगर हम कोई दो आर ले और उसके
ये बना लेता हूँ, ये मैंने बना दिया। आप बताएं।
सर कोई भी दो रैंडम अगर आर हम ड्रॉ करते हैं
एक आर वेक्टर ड्रॉ करो। You switch from English to Urdu and have the class switches off. And then when you switch back to it, then the other half switches off. The question was, why physically is that equation hard? आप क्या करें?
इसके अलावा यूनिट वेक्टर है वो ये आता है।
कहाँ पे बनाओ? ये यूनिट वेक्टर बना दीजिए, ये याद बना दीजिए। आप क्या करेंगे? क्या चीज शो करती है कि ये इक्वेशन ट्रू है?
सर दो पॉइंट
Again, all of that homework, draw all of these equations in terms of figures like these. And also sort of tell why there are these factors of 1 over r, try to sort of sort that out. Okay, by the way, using these equations now, these equations, 4 equations that I've written over here, now you can do that homework. Partial by partial theta of EX is equal to 0. Right? Prove that. Don't just go like this. Let me erase that. Let's partial by partial r of v. Right? Now we can do this. Since we know all of those equations, right? So now I can write like this. Partial by partial r, and this is vr plus v theta, right? And so this becomes partial vr over partial r, er plus vr, partial er over partial r plus v partial d theta over partial r, d theta plus partial d theta partial d theta over partial r. And since you know all four of these, you can calculate that. Both of these, you can calculate this. So a better way of writing this would be partial by partial r. V would be partial by partial r, v alpha, e alpha, and so that would be partial v alpha over partial r, e alpha plus v alpha partial e alpha. I mean, it's the same thing. But if you want to completely generalize that, you could write it like this: partial by partial x, whatever, beta, let's say v. So that is going to be partial v alpha over partial x beta, e alpha plus v alpha. Okay. So, and another notation that you guys are used to is that this is partial alpha comma beta e alpha plus v alpha, and this is partial v alpha over partial.
So,
Yeah.
in this general form, x could take values of r. X could be r and theta, right? If you're considering polar coordinates.
Say again?
In this general form, x could be r or theta if you're considering polar coordinates, right?
Oh, yeah.
Similarly, alpha and
Yeah, this is the same.
also be r and theta.
Yeah, that's the same issue.
Polar coordinates.
Yeah. When we write, yeah, these are just coordinates. These are just coordinates.
So alpha and beta would also be r and theta, right?
Yeah, yeah. Yeah.
Not necessarily.
If we're considering polar coordinates.
If we could take for coordinates, yes.
Could be anything.
Yeah.
So we're not to use.
I think what you want to say, and I think the problem that she has, is that when you are differentiating, right, you are differentiating with respect to things which have different dimensions, right? Differentiating with respect to r, and then differentiating with respect to theta.
That's covered.
Yeah, that's covered.
Those dimensions that I
Yes.
have in
Those in the basic vectors and stuff.
So we do not use their common notation for the basis for the basic vector.
Say again?
We do not use this common notation.
Yeah, we could. No, we don't. When we have vectors, we don't do that. This is usually written just in terms of components. Yeah, that's why I didn't write it like that. But the thing is that for a given beta, for example, if it is r or theta, right? These are the components of a vector. These are the components of a vector, and these are the components of a vector, and this must be a vector, right? For a given. If this is a vector, then I should be able to write it as a linear combination of the basis vectors, right? Any questions there? So, for example, so this partial E alpha over partial X beta, this is, this can be written as a linear combination of all the basis vectors, right? And of course, as you change the basis vector here, this number would change, and this beta, if you change the coordinate with respect to which you are differentiating, then this will change. And so, you have this equation. Okay? These things are called Christofle symbols. Why don't we call them Christofle's tensors? Because they're not tensors. and that's why they're symbols.
So why are they Christofle?
Yeah, why are they not tensors? I mean, you're writing alpha, beta, mu, things which are so characteristics of tensors.
So we have to show that they are tensors.
Yeah, we'll have to show. So if you put something on, I mean, like mu or mu, things which sort of give you components, which take on different values, I mean, what do you call these? The indices. Doesn't necessarily mean them tensors.
They need to transform it.
They need to transform like a tensor, right? Yeah.
सर ये वाला काम करके उसको टेंसर नहीं बना सकते। ये जो आपने किया इनवर्स
Yes, very good question. वो ये कह रहे हैं कि अगर वो टेंसर नहीं है तो ये वाला काम करके टेंसर बना रहे हैं। जैसे तुमने ये ऐसी बात की है कि इनमें से आधे बेहोश होने वाले हैं। इसको समझ नहीं आया तुम क्या कह रहे हो? दोबारा करो।
मतलब जैसे ये भी वेक्टर है।
कौन सा वेक्टर है?
ये जो है आपने ट्रांसफॉर्म किया जो
ये सारी चीज एक वेक्टर है।
पूरा वेक्टर है।
ठीक है?
तो हम इस तरीके का कुछ मैट्रिक टेंसर
ये सारे नंबर्स हैं और ये वेक्टर्स हैं, राइट? सो ये जो लीनियर कॉम्बिनेशन है वेक्टर्स का, ये एक वेक्टर दे रहा है। वैसे अभी हम ये कह रहे हैं, बात तो ठीक है, वो ये कह रहा है कि अगर ये वेक्टर है तो आपको मसला क्या है? अभी आप कह रहे हैं वेक्टर नहीं, टेंसर नहीं है, कह रहे हैं वेक्टर है, टेंसर नहीं, तो हर वेक्टर टेंसर ही होता है। तो फिर क्या मसला है? बेसिस वेक्टर वेक्टर है, ठीक है। तो भी ठीक है। ये सारी बातें अगर आपको समझ नहीं आ रही, आप में से किसी को भी समझ नहीं आ रही, then you really need to look at tensors. ठीक है? जब हम मुख्तलिफ चीजें हैं, वेक्टर्स हैं, टेंसर्स हैं, फिर बेसिस हैं, फिर उनके कंपोनेंट्स हैं, ये सारी मुख्तलिफ चीजें हैं, ठीक है? वेक्टर और टेंसर ट्रांसफॉर्म नहीं होते। अगर आप बेसिस चेंज कर दें, सॉरी, अगर आप कोऑर्डिनेट्स चेंज कर दें, तो वेक्टर वेक्टर ही रहता है, वैसे ही वेक्टर रहता है। इसकी एक एग्जांपल ये है कि अगर मैं इसको ऊपर फेंकूं तो इसका इस पॉइंट के ऊपर कोई वेलोसिटी वेक्टर है। आप कहते हैं जी इस कमरे के अंदर एक्स वाई कोऑर्डिनेट्स है, वो कहता नहीं मुझे पसंद ही नहीं है, मैं तो आर थीटा फाई यूज करूंगा। उसका मतलब ये वेक्टर चेंज हो गया? वेक्टर तो चेंज नहीं होगा, फिर चेंज क्या होगा? कंपोनेंट चेंज हो गए, राइट? सो जब हम कहते हैं कि ये वेक्टर है तो ये स्टेटमेंट इस बात से बिल्कुल मुख्तलिफ है कि ये क्या चीज है, ठीक है? क्या ये किसी टेंसर के कंपोनेंट्स हैं या नहीं है, ये क्वेश्चन है। आंसर ये है कि नहीं है। अगर इनके ऊपर इस तरह की चीजें पड़ी हुई हैं, जैसे अल्फा, बीटा, म्यू, न्यू इंडिसेस पड़े हुए हैं, but that does not make it a tensor because it doesn't transform like a tensor. अच्छा, एक और बात यहाँ पर, एक अभी मसले में मसला है, ये ट्रांसफॉर्म होता है टेंसर की तरह। ये तो आप लोगों को ने शो किया था कि जब आप पार्ट दोबारा करो, अगर कोई स्केलर फील्ड है, अगर स्केलर फील्ड को हम डिफरेंशिएट करेंगे तो हमें एक रैंक हायर का टेंसर मिल जाएगा, यानी वन फॉर्म मिल जाएगा। लेकिन अगर हम वेक्टर को डिफरेंशिएट करेंगे तो 0 2 वेक्टर या 1 1 टेंसर नहीं मिलेगा। क्यों? बाय द वे मिलेगा अगर आप कार्टेशियन कोऑर्डिनेट्स में,
ये से कार्टेशियन कोऑर्डिनेट।
तो क्यों? फिर यहाँ पे क्या मसला पड़ गया?
बेसिस ट्रांसफॉर्म हो गई, मतलब अब ये वाले जो कंपाउंड से मिला के एक टेंसर बनाते हैं, पर इंडिविजुअली दे नॉट टेंसर।
यहाँ पे गड़बड़ है, स्टेटमेंट में गड़बड़ है। You can show whether this transforms like a tensor or not. This does not transform like a tensor. अगर आप कार्टेशियन कोऑर्डिनेट्स में रहें और कोऑर्डिनेट्स को सिर्फ रोटेट करें, एक से रोटेट करके दूसरे में चले जाएं, लेकिन रहे आपका कार्टेशियन कोऑर्डिनेट्स, then this is a tensor. Under only those transformations, this is a tensor. But in general, this is not a tensor. Can you show me why? ये देखें, अगर आप इसको इस नोटेशन में लिख लें ज़्यादा आसान हो जाएगी। डी बीटा बी अल्फा, ये है ना? So it better transform like this. Lambda v beta lambda Is this equation true or not? अगर तो ये इक्वेशन ट्रू है तो ये टेंशन है। अगर ये इक्वेशन ट्रू नहीं है, अच्छा मैंने दोबारा वही काम किया। राइट? अब पहली बात ये है कि इक्वेशन ट्रू नहीं है। इक्वेशन ट्रू क्यों नहीं है?
जब हम इसको ट्रांसफॉर्म करते हैं इसके कंपोनेंट्स को और फिर उसके डिफरेंशिएट में लगाते हैं तो जो हमारा ट्रांसफॉर्मेशन मैट्रिक्स है वो भी मतलब
दैट्स एग्जैक्टली राइट। सो अब आप इसको देखें, ये क्या चीज़ है? इसको ट्रांसफॉर्म करने के लिए तो कोई मसला नहीं है, आप ये यूज़ कर सकते हैं। ये ट्रांसफॉर्म हो जाएगा, ठीक है? तो आप इसको ट्रांसफॉर्म करेंगे तो ये बनेगा अल्फा बार अल्फा बी अल्फा। अब जब ये इसके ऊपर अप्लाई होगा तो ये क्योंकि ये इन जनरल कोऑर्डिनेट्स का फंक्शन है, ये दोनों डिफरेंशिएट होंगे। सो एक टर्म तो आपको मिल जाएगी जो ऐसी होगी, लेकिन एक एक्स्ट्रा टर्म आ जाएगी। सो दिस थिंग इज एल बीटा बीटा बार डी एल अल्फा बार अल्फा डी बीटा बी अल्फा प्लस L beta beta bar V alpha D beta L alpha bar. This thing is not in general 0. लेकिन अगर आप सिर्फ कार्टेशियन में रहें, एंगल जो है वो कांस्टेंट है, that will be 0. Any questions here?
Sir? Can you tell me Christofle symbol किस तरह है तुम्हारा? I see we are writing a vector as a linear combination of the bases.
Yes.
But how exactly are we getting this symbol and what is it?
This is just I mean, I could write it like this. I could write it like this. Wait, I could write it like this. Let's say that this is 1 and this is 2, right? And so this is a vector. So then this will be an alpha 1 E1 plus alpha 2 E2. Do you agree with that? Right? So then this thing would just be gamma 1, 1, 2. We just generalize this equation. And this would be gamma 1, gamma 2. Gamma 2 होगा? हाँ, भी इसके साथ ना ठीक है 2, 1, 2. ठीक है? So अगर आप इसको जनरलाइज करके लिख दें और ये पार्शियल ई अल्फा ओवर पार्शियल एक्स पार्शियल बीटा ई अल्फा हो तो ये हो जाएगा म्यू, ये इसके ऊपर सम है ना, क्योंकि ये सारी बेसिस आएगी और इन दोनों के लिए है तो ऐसे करते हैं। अच्छा, यहाँ पर ना ये जो ऑर्डर हम रखते हैं ना, ये कुछ भी रख सकते हैं और क्योंकि ये टेंशन वगैरह नहीं है, ये सिंपल्स ही हैं, लेकिन एक दफ़ा जब रख लें then you don't change it. In the end we'll be able to prove it that is symmetric in these two symbols. लेकिन अभी तो हमें नहीं पता, अभी नहीं पता। अच्छा, अब अगर आपको अब जैसे अगर आपने ये निकाले हुए सब, ये सारे डेरिवेटिव्स आपने निकाले हुए, राइट? निकाले हुए ना? इनको देख के क्या आप सारे क्रिस्टोफल सिंबल निकाल सकते हैं पोलर कोऑर्डिनेट्स में? ऑफ कोर्स निकाल सकते हैं। मिसाल के तौर पर अच्छा, सो पार्शियल ई आर over partial R, this was 0. Mariam, कौन सा R क्रिस्टोफल सिंबल यहाँ से मिलेगा?
How do we write something?
नहीं नहीं, बस यहाँ से एक क्रिस्टोफल सिंबल का पता लग रहा है, बल्कि दो का पता लग रहा है। कौन कौन सा है? He's like me. Yes, of course you. Go ahead. हाँ उस बात में
सर नीचे दो आर होंगे, ऊपर आप एक आर लगाने पहले फिर आप अगले वाले में
थीटा लगा, राइट? सो यहाँ पर R आएगा, ये भी 0 है, और थीटा आएगा और R आएगा, ये भी 0, ठीक है? कैसे? ये कैसे पता चले?
So if we write it as a linear combination of ER and
हाँ, बताओ कैसे लिखेंगे?
E.
सो ऐसे लिखेंगे कि एक ये वेक्टर है ना, एक ER के साथ टर्म आएगी, वो R आएगी, और ये दोनों R है तो ये R आ गया, ठीक है? एक टर्म थीटा के साथ आएगी, तो यहाँ पे थीटा आ गया, यहाँ पर R आ गया। अब ये दोनों 0 तो ये दोनों 0 हो गए, ठीक है? आता है? So homework, calculate all Christofle symbols because you know all derivatives. Let me just write down this last thing. And so partial by partial x theta, right? This thing, if you just happen to, just look at this. So this is coming here. So this thing is V alpha comma beta E alpha plus V alpha and then gamma mu alpha beta and E beta or E mu. Is that right? Yeah.
सर उधर वो जो क्रिस्टोफर सिंबल है वो 1 हुआ क्या? वो वहाँ पे क्यों नहीं?
कहाँ पे?
The first term, so on the right hand side.
यहाँ पे?
Yeah.
यहाँ पर ना? हाँ जी, तो बताओ। She's like, please why you ever ask me anything? Do you not want me to come to class? Yes, Isabella. Did you understand his question? तो क्यों वो वहाँ पे क्यों नहीं लिखा? 1 कैसे हो गया?
सर उधर पहले ही बेसिस वेक्टर था, इधर भी बेसिस वेक्टर चाहिए था, तो हमने इस साइड को
जब आप डिफरेंशिएट करेंगे तब आएगा। बाकी तो पहली टर्म तो मैंने वैसे ही लिख दी है जैसे वहाँ पे लिखी हुई है, राइट? तो ये आएगा यहीं पे। अच्छा, अब यहाँ पर हमने ना ई अल्फा को बाहर लेना है, सो वी वुड वांट टू, ये डमी इंडिसेस है, सो आई कैन जस्ट ई गामा और इसको मैं अल्फा कर देता हूँ, ठीक है? किसी को इतराज तो नहीं हुआ, राइट? एंड सो दिस बिकम्स वी अल्फा, इतराज वालों से पूछा नहीं मैंने, साथ ये क्या हुआ?
आपने डमी इंडिसेस के नाम बदल दिया,
ठीक है? समझता नहीं? Okay, so alpha, gamma, beta, V gamma, beta. Okay, so for a given beta, this is a vector, this must be the components of a vector. But now there is another question. If you take beta to be an abstract index, because beta has values 1 and 2, right? So then this looks like as if these are the components of a 1-1 tensor. The question is, are they? And what do I have to do to show that this is a 1-1 tensor? These are the components of a 1-1 tensor.
So it doesn't look like a 1-1 tensor because if beta takes a concrete value, for that case we only have alpha.
For that case, we know that these are the components of a vector. Right? अगर मैं यहाँ पर partial v by partial r कर दूँ, यहाँ पे r आ जाएगा, यहाँ r आ जाएगा. These will be the components of a vector. In order to show that, you will just have to say whether it does or does not transform like a 1-1 tensor. Right? So we'll talk about that next time. We're at the cusp of a discovery here. Any questions?
Will not be more accurate to say that the specifying the anything measuring tensor tells us the way space looks, because our notion of points that are far away and those remain the same.
Yeah, we call that finding the metric.
When you study metric spaces in mathematics, the notion of the common notion of points that are close to each other and they are far apart between. We could say that we define a metric that would say that all.
Okay, let's not talk about whether this gives or that. Let's just talk about how do you put structure in spaces. Right? Okay. So, for example, if you have a line, if you have and a line is parameterized by a continuous parameter, right? So and so just the real number, all of the real numbers, right? Okay, fine. So until now you don't have a metric on it, but you know which point is next to which, right? So then I say, oh, here's an idea for a metric. Why don't you just take the sort of the number of the number, one number, and subtract it from the number of the other number of the other point, and that will give you a metric, right? As soon as I've done that, now you have more structure. You know how far these points are, right? Or I could say if the number between 2 points is less than 1, call it 0,
Yes.
or if it's bigger than 1, call it 1,
Yes.
something like that. That would give you a different structure on the same line. Right? So initially when you put points together, you know which points are where, but you don't know the distance between them. Right? So then you say, oh, but I want a differential structure. Because I want to be I'm so used to doing physics and continuum that I want to be able to differentiate things. I don't like when I don't differentiate. I've studied calculus for like 3 courses. I need to use it. So, okay, then you want a differentiable manifold. So then you say that the curves, when you take tangent vectors, at every point, not only that the tangent vector is defined, but if you come to that point from different directions, you get the same sort of tangent vector or whatever. And so you just find this is a differentiable structure. Then you say, oh, I want to be able to say which point is farther away or which point is closer by, and you put a metric on it. And so, or you could say that you could put a metric up to a conformal factor. Let's say, don't define the conformal factor, I think I'm right. Then you would be able to say the angles and the shapes, but you won't be able to tell exactly how big or small they are. Then you specify the conformal factor as well. And then now you can actually exactly say everything. All of the geometrical properties of the space are given like this. So that's sort of the layer. And then there's something called complete spaces or normal spaces between topological spaces and metric spaces or something like that. There are other structures as well, so I'm not giving you the complete as mathematicians are very clever with that. they have made more steps. And so there is all this structure that you sort of put on a space before it gets the complete shape. So we say that the anti-momentum tensor gives you the vector, the complete shape. It's not just a single component vector or not just a By the way, when we say metric, our metric is not usually the metric that mathematicians are very fond of. It's not positive definite. And so, yeah, mathematicians don't like us. What's wrong with you guys? Why can't you just keep the metric positive definite? Yeah. Any more questions? Okay, so I'll send the homework to Junaid and he will email it to you guys. Most probably it's just going to be some questions of chapter 5. This is chapter 5, right? Some questions of chapter 5. In fact, just look at all of the questions. This homework will be collected and graded, but you guys just go ahead and start solving questions.